Hello everyone, and welcome to this screencast. I'm going to talk a little bit about a very recent technology that Intel and Micron co-venture announced middle of 2015 and demoed at the Intel Developers Forum in Shenzhen in 2016. This technology is called 3DXPoint. The technology has the potential to replace the good old, well-established NAND flash memory and extend the performance capacity of the device while potentially lowering the cost of the manufacturing. In this day and age, research in device and manufacturing scaling driven by macroeconomics and markets worth of tens of billions of dollars for storage, servers, client PCs, and handheld devices is taking unprecedented measures to keep more or dinar scaling in full steam. And NAND flash has to keep up, but it's a gigantic challenge. The cell designs have evolved in the last 2 decades a lot to continue the scaling of the DRAM and the NAND to 20 nanometer and below to 16 and even 14. But essentially the operation or the physics of both technologies have remained mainly the same. And so they are now facing today a very hard technological limitation to keep on scaling. Now let's learn a little bit more about the NAND technology and why has the semiconductor industry been very hard at work trying to find a contender technology to improve upon it. At the heart of the NAND flash memory is a floating gate transistor. This is the unit cell or the basic building block that builds the NAND, and this is what I'm showing here. What we have here is basically a control gate, and then we have an interpoly dielectric, this layer, and then we have a floating gate, titanium oxide, and then the bulk. The bulk is consisting of a drain and a source and silicon. This is where we're getting the charges from. So let me draw the charges here with a different color. This is the red here. So we have this charges, negative charges. These negative charges are supposed to tunnel through, these are electrons, and they're going to charge the floating gate. And to erase the voltage that is accumulated on the device, we just have to allow the electrons to tunnel back from the floating gate back to the source. And that changes back the V threshold to whatever the value of the V threshold at level 0 was, and that's how we make the difference between a level 0 and level 1. Now, what we know, however, is that the 3D NAND is kind of a very complicated process, right? So we know from, if the lectures in E292L, what we have seen that the process to fabricate the BICs and the PBICs was Toshiba is pioneering, and the TCAT of Samsung is very, very complicated. It requires very directional etching, for example, to fill the channel material, to firstly etch and then fill the channel material. And then we know that the operation itself is actually very involved. So in here, for example, because the NANDs are all stringed together like that in a series manner, we have to have a lot of control lines to get the chunk of information that we are interested in. So we have to have the bit line, we have to have the source line, we have to have a lower select gate, control gate, and upper selection gate. And that increases, that makes the operation with the external circuitry that is required to control the NAND not very simple. Right. So, given that, there are a lot of alternatives that have been proposed over the years, and they are being in the research works. They are being researched. So we are looking at the STT, the spin torque transfer, magnetic RAM. We have the phase change memory RAM. We have the resistive RAM. And then we have the very futuristic ones that are very far out, that might be based on the carbon nanotubes. Essentially, the NAND suffers from two mechanisms that threatens its endurance. We have number one, stress-induced leakage current that could be because of charge trapping in the dielectric that eventually can lead to threshold voltage degradation, like what we see here in this graph. Say, for example, for a single level cell, we have the level 0 and the level 1 here. We have the level 0, we have the level 1 marked at +2 and -2. Plus and -2, and we say that after 10 to the 3 or 10 to the 4 programming and array cycles, we see that the threshold voltage is kind of, it's not keeping up, constant, but eventually it degrades and it changes its value. And at some point, after a critical point, we see that once this value is past 0, that's where the logic cannot differentiate between if it's a 0 or a 1, and that's where you have retention errors or reading errors, basically, that says, well, I wrote a 1, but I don't know if this is a 1 or a 0, right? So that is a stress-induced leakage current. During arrays and program operations, the electric field strength across the tunnel oxide is very high. It's multiple million voltage per centimeter. So we're talking about in the order of 10 to the 6 voltage per centimeter. Such high electric field strength can lead to structural defects that trap electrons in the oxide layer, and over time, these defects accumulate, and the tunneling current can lead to shifts in the threshold voltage, as we explained here. Now, we can actually calculate from this law right here, we can actually calculate the number of times that we can do a programming or erase, depending on the geometry of the dielectric from the area, and the charge that we are allowing in, and the delta V that we are applying on the dielectric itself, right? And so the comparison here is very clear between the single level and the multi-level, tri-level, and the quad level. We can see that there can be retention errors over time, over the 10 to the 4. So this is all the question of endurance. Of course, we should have known that the industry is going to find an alternative. They're not going to pretend that the problem does not exist, and everybody in the industry would be very happy to find an alternative. Nobody would be a naysayer protesting against the new technology. So that brings us to the 3D XPoint technology. Intel Senior VP Rob Crook announced the next generation 3D XPoint. He said it will dwarf the NAND technology in terms of endurance, speed, and density. Intel claimed that Optane, or the new XPoint, is a breakthrough technology that will deliver up to 1,000 times the performance of flash memories. It will be the biggest breakthrough in memory technology in over 20 years, using some unique material compounds that they have developed over the last decade or so, and a crosspoint architecture. The crosspoint architecture is essentially the wires that are overlaying in a perpendicular way, functioning as a word line, say for instance this guy, and a bit line right here, to do a selection and read the value that is stored in this memory cell. We have the memory cell is a selector and a memory cell that does the connection between the two and reads the value that's stored. The density is so high, it's by comparison to the DRAM, it's about 8 times or 10 times. And what's interesting here is that the physics of this device are quite different. There are no transistors here, folks, which means we gain in terms of cost, density, and process complexity. Large memory capacity or very fast storage can leverage this technology. Think about the application that can benefit from this speed gain. Genome sequencing, deep learning, pattern recognition, real-time tracking of diseases, and immersive 8K gaming. So let's see here a quick comparison between the DRAM, the 3D XPoint, and the NAND. So let's see here on this slide, Intel is saying, they are claiming that 3D XPoint is going to be 1,000 times faster than NAND, 1,000 times more endurance by comparison to the NAND, and 10 times denser than conventional memory. What does this translate to? That translates to DRAM. By comparison here, we have the DRAM, as we know, has a 10 to the 15 times of program and erase cycles. The 3D XPoint is going to have 10 to the 7, right, by comparison, and the NAND has never been higher than 10 to the 3 or 10 to the 4, if you're very, very optimistic. Now, in terms of latency, we're talking here, the DRAM has very, very close to a few nanoseconds, even for the slowest process, which is probably the writing, just nanoseconds. And then the 3D is a little bit of tens, somewhere in the teens, say 20 nanosecond perhaps, and then the NAND is on the order of microseconds, which is extremely, extremely slow by comparison to these two applications, 100 microseconds. What's even more interesting, guys, is that the memory can be integrated on top of standard CMOS logic on the same die, so no separate packaging is needed. 3D XPoint, if used as a system memory instead of DRAM, can shave off a lot of memory access latency between the system on chip and the LPDDR chip, for example. There is no TM cross-section image for the device that Intel and Micron the Intel and Micron have announced, but we have from Unity Memories. They have released a TM image, which is shown right here. You can see between these two lines here, this one line and this one line, you have two separate memory layers, which they brand as CMOX. It's a competitor to the Intel and Micron 2 CMOX. And then in here, you just have the simple, CMOS logic. So the CMOS logic would be stopping right here. That would be the memory, and that would be the end of the package. This is very similar to what we have seen in the previous slide from Intel. We have the bit lines, we have the word lines, and then we have the selector, and then we have the memory cell shown here in light blue, right there. Although neither Intel nor Micron have published widely about the fundamental technology behind the 3D XPoint, we do actually know that the device is essentially a version of the resistive RAM that works by modifying the resistance level of the bulk in a cell, and that in turn changes the amount of current that goes through and thus differentiates between 0 and 1. Applying a specific voltage on the word line and the bit line will activate a single selector and enables the cell underneath to be either written to or read from. We are most likely looking at a spintronic device actually. Either it's a spin crossover or a spin transfer torque. So let's go over these two mechanisms really quickly. In a spin crossover, let's consider for spin crossover a transition metal. Here's an iron molecule with a 2+ environment with its main bonding orbital is called T2G, and the lower energy right here, and the higher energy is called Eg. What we have, due to Pauli's exclusion principle, each of the 6 electrons are paired into 3 orbitals, and each pair of electrons has 1 spin up and 1 spin down, as we can see. 1 spin up and 1 spin down for every electron. This is the ground state, also known as the low spin state, as the total spin S is equal to 0, because everyone is canceling each other out. Right? The spin of the electron is half. There is a plus half, there is a minus half. They both cancel each other out. The other mode for this atom is the high spin state, where the 2 electrons move to the higher bonding orbital, giving a total spin of 1. Right? So we have a spin up, we have a spin up, and that's the other state. Now, in the spin crossover, compounds can be directly applied between junctions, and their resistance can be changed. So we can see here an example. This one is a carbon nanotubes, but essentially the idea is the same, right? We have a junction on the left, we have a junction on the right, and we have electrons going through, and depending on what is the state of the junction on the left and what is the state of the junction on the right, we can allow current going through, or we cannot allow. There will be no more current in this case, or we will have a current that is going in that case, because that changes the resistance from the left to the right. On the other hand, in this case on the right, which we call a spin torque transfer, relies on a feature known as a spin polarized current, as a SPC. It's a spin polarized current, SPC. Now, electrons intrinsically have spin in 2 directions, up or down, as we have covered before. An electric current typically consists of an even mix of these two, giving an overall unpolarized current, no overall spin direction majority. When an unpolarized current is passed through a thick layer of magnetic material, this is going to be our magnetic material, it causes the current to become polarized. If this polarized current then passes through a thin magnetic layer, the thin magnetic layer is going to be the free layer that we control. With a different density of electron states, the polarization of the current can cause the magnet to flip, right, due to more electrons relaxing into states of opposite spin. With a thick layer having constant magnetic orientation, here is the reference layer, or the thick layer would always have a constant magnetic direction right here. And the thin layer, or the flare, being able to flip. This guy right here, the one on the bottom, could be going to the right, could be going to the left. Depending on the material, the resistance between the 2 combinations can act as a memory cell. There is another approach how we can construct this memory cell. We can use something called conductive bridging. In a conductive bridging cell, a thin film of electrolyte, and this is the film right here, historically could be a liquid or a solid, is between this iron reservoir and a dielectric. When a negative bias is applied to the inert electrode, the metal ions in the electrolyte are reduced to form metal atoms. When enough of these metal atoms are reduced and connected, it forms a wire between the 2 electrodes, and that's what you see in the golden, in this caricature, the golden wire, or you can see as a stub between these 2 layers in the TEM image. It forms the wires between the 2 electrodes. In order to break the wire, the reverse potential difference is applied, and the atoms in the wire are oxidized to become part of the electrolyte back again. And that basically changes the resistance between being conductive or non-conductive, and so on. And that's how we can see a 0 and a 1. So I think I'm going to conclude my presentation here, and what I would like to leave you with is the announcement of Intel, as Intel has granted it, they have said that there has not been an announcement of this magnitude since 1989 when the NAND memory was introduced. They have improved and scaled a lot of over the decades, but the architecture have not essentially changed. And so the 3D XPoint is really a new class of memory. It's fast, durable, scalable, non-volatile, whereas the DRAM and NAND each only meet two of these criteria. So Intel have really